Hello, my friends. I'm recording, right? Yeah, it's working. Okay, how are you doing today? Um, Hope you're fine. I haven't been recording for a long while just because I've been really busy. I still am now, but maybe I'll be a little less busy in a few months, but we'll see. So this video is about Ramanujan summations, and it has quite a comical title, as you can tell. Proof that you have no Rizz. What is Rizz now? Um, for those of you who may be older than 25 and don't care about the young people's terminology, and I respect that, but those of you who don't, this just means charisma, right? Just it's the same thing as charisma. That's what Riz means, essentially. Um, some people translate it slightly differently, but that's what I would define it to be. So, how can I prove that you have no charisma? Okay, let me use Ramanujan summations. So, I'm going to introduce this topic to you as this. So let's say you have following sum. Sum as some index is called a z, goes from 1 to infinity of some function of z, right? This, in other words, can be written like this in its open form: f of 1 plus f of 2 plus f of 3. Indefinitely many terms there. F of infinity. We can't even write infinity in that way, so let's write it like this. Um, This is according to Ramanujan's summation. We can equate this infinite sum to negative f of 0 over 2 plus I, lots of the integral from 0 to infinity of f of it minus f of negative it over e to the 2 pi t minus 1 dt, where of course I is defined to be the square root of minus 1. Let me just write here. I equals root minus 1. In other words, I squared equals minus 1. Just an imaginary number. It's a really special number to me, but to a lot of you guys, you probably don't care. Now, the next thing I'm going to do is, let's see, let me just, okay, my app was glitching there, but, I'm going to show you a simple example. Actually, no, before I do that, I need to give you a few conditions for this summation to work. I forgot about that. So firstly, of course, f of 0 has to be defined. If it's not defined, then unfortunately this summation won't work. For example, if you have f of x to be 1 over x, well, f of 0 is just undefined. So, that's where this summation may fall apart, so you have to be careful. The next thing you have to be mindful of is that the original sum from 1 to infinity of f of z has to be divergent. So in other words, it diverges, or it goes to infinity or negative infinity, or it doesn't reach a particular value at all. One classic example of this is 1 minus 1 plus 1 minus 1 plus dot dot dot. This sum doesn't reach a particular value, it just oscillates back and forth. In our case, um, we need our sum to be divergent. Otherwise, if it's convergent, then this summation formula falls apart. In other words, the Ramanujan summation is a way to assign finite values to infinite sums or to divergent sums. Finally, the integral of f of it minus f of negative it all over e to the 2 pi t minus 1 dt also this one actually has to converge, has to be convergent, right? Otherwise, once again, the sum just falls apart. So I think those are the conditions that need to be fulfilled in order for this summation to actually work, right? So f of 0 has to be defined, the sum has to diverge, and the integral has to converge. Okay, now let me show you a simple example, then we will construct the proof that you have no Rizz. So a simple example could be something like the sum of 1 plus 2 plus 3 plus 4 plus dot dot dot. Of course, in a real number or in like a calculus context, this just goes to infinity, right? But according to the Ramanujan summation, this is equal to negative a 12th. And it looks funny at first. It's so counterintuitive, but I'll show you why. So in this situation, we're having that the function f of z equals z, right? This is quite simple. If you put in a number 1 into z, the function will spit out a number 1 back at you. Same with 2, 3, 4, etc. So in essence, we have the sum as z goes from 1 to infinity of z. That's what f of z is. This, according to Ramanujan's summation, equals negative f of 0 over here, as I written here. Negative f of 0. In this case, f of 0 is just 0, and then that's over 2, plus I lots of the integral from 0 to infinity of the numerator, according to what I've written already, is f of it minus f of negative it. If you put it into the function, it will spit back the exact same thing, it. If you put negative it, it will give you back negative it. The rest of the integral is just e to the 2 pi t minus 1 dt. Cool. And this 0 is just 0. We can ignore that. Now, before we continue, does this function f of z fulfill these 3 criteria? Well, the first criteria was f of 0 was defined. Is that the case here? Well, we've defined it to be 0, so it is defined. Secondly, the sum has to diverge. In our case, it definitely diverges. It goes to infinity. So yes, the sum diverges. And the integral, does that? We don't know yet. Let's just see what happens. So we end up with I lots of the integral from 0 to infinity. Let me just write the denominator as is, and same with dt. Now the numerator, it minus negative it, it's just equal to it plus it, which is 2it, right? I'm going to put the 2i like this, and then the t in black like that. Now, 2i is just a constant, and it's a scalar constant, so we can just factor it outside the integral. So we get the following. We get 2i multiplied by the I that was already there times the rest of the integral. Okay, so nothing's changed. We just put the 2i outside. And this thing here that I've underlined is 2i squared, which is negative 2, right? So negative 2 there times the integral of all of this. And what does this integral actually turn out to be? Let me just work out this integral on its own. I mean, I'm not going to work it out fully. I'm going to take a substitution where you let u equal to 2 pi t, which was, by the way, the exponent which the e is attached to. And so if you differentiate both sides, you'll eventually get du over 2 pi equals dt. Now, I don't want to turn this into a calculus lesson or anything, so I'm not going to go through the eensy details of calculus today, even if that is my favorite subtopic of maths. But yeah, on the numerator, t will be replaced with u divided by 2 pi. On the denominator, e to the 2 pi t will be replaced by e to the u. The minus 1 stays the same. Dt will be replaced by du over 2 pi. And if you work this integral out, this 2 pi here and this 2 pi, they're just constants, so we can factor them out like this. And then you're left with the rest of the integral from 0 to infinity of u over e to the positive u, sorry, not negative u, minus 1 du. I was being distracted by the Gaussian integral there, so I nearly said negative u squared, but there we are. And this, by the way, I won't go through this integral today. This may be for another video. Don't want to spoil too much, but this integral is actually just pi squared over 6. This is the basal problem, the basal problem, whatever you want to translate it. So we end up with 1 over 4 pi squared times pi squared over 6. You can use Wolfram Alpha. You can go on YouTube, find this, and the integral ends up being 1 over 24. If we put this result back there, well, we get negative 2 times 1 over 24, which is negative a 12th, and exactly matches up with the statement I made earlier, that the infinite sum, 1 plus 2 plus 3 plus 4 plus ... equals, according to Ramanujan's summation, minus a 12th. Okay, cool. Now that I've shown you a simple example of this with the most basic function that I could think of, which was f of z equals z, a sketch of that if you're interested, where this is the z-axis and this is f of z. It's just going to look like a straight line going through the origin with a gradient of 1. That's quite a simple thing there. Okay, now I'm going to construct the proof that you have no Rizz. This is what the climax of the video is, what we've been building up to. So we have 3 cases really here. So let me go through what all these cases have in common. There's going to be a sigma there. There's going to be a Rizz inside the sigma, like this, Rizz, yeah. There's going to be an index going from 1 to infinity, as the Ramanujan sum applies to these indexes. But there's 3 different letters, so we have 3 different cases. One case where z is our index, another case where I is our index, and where r is our index. So in the case where z is our index, I'm going to define I to be the square root of -1, and I'm going to define r to be a positive real number, right? Okay, cool. Now, the reason I'm defining r to be positive real is because r is usually like a radius or like the argument of a complex number, which is always a positive. It's a magnitude, basically. So that's why I'm defining r to be a positive real. Now, in the second case where I is our index, I is no longer the square root of -1, it's just the index. So if you've done stats before and you've seen this type of notation, this thing here, sigma as I goes from 1 to n of xi, I is just the index. You get x1 plus x2 plus ... plus xn, right? That's just if you're into stats, by the way. I'm not, personally. I'm not a big fan of applied maths. I believe in the concept of I make the mathematical theorems, axioms, whatever I do, and I give them to a physicist who will use them for his own purpose. Anyway, I is the index here in this case. R, I'm going to still define it as a positive real number, and I'm going to define z to be just a real number. In other words, z squared is positive, or it's greater than or equal to 0, basically, because all real numbers squared give you 0 or greater, right? If you go to complex numbers, some complex numbers may square to a negative number, such as I squared is -1, but you'll see why later on when the proof is being constructed. When r is our index in our third case, I'm going to define I to be the root of -1 and z to be a real number, or that z squared is greater than or equal to 0. Cool. Now that we've got our 3 cases done, let's go through all of these cases one by one, apply our Ramanujan summation to each of them, and prove that you have no Rizz. So let's work with number 1 first, where z is our index. So we have the sum as z goes from 1 to infinity of r, I, z, z, sigma Rizz, is equal to sigma as z goes from 1 to infinity of, I'm just going to tidy up a little, riz squared. It's just the same thing. Z times z is z squared, which according to Ramanujan is equal to negative f of 0 over 2 plus I, lots of the integral, of f of it minus f of negative it over e to the 2 pi t minus 1 dt. In our case, our function, let me just put it in blue, f of z is equal to riz squared. Cool. So if you plug 0 into our function, f of 0 is equal to ri times 0 squared, and the rest is just like that, plus I, lots of the integral from 0 to infinity of, I'm just going to put the denominator down, that's just the same. The numerator now, that's what's interesting. F of it minus f of negative it. Well, let's work on that on the side. F of it minus f of negative it equals to, by the way, f was just riz squared. F of z is riz squared. Replace z with it, you get rit squared minus f of negative it, which is ri negative it squared. Now, this fact I'm going to tell you holds true for all real and complex numbers, that a squared is just equal to negative a squared. This is because negative a squared can be written as negative 1 squared times a squared, which is negative 1 squared is just 1, so we get a squared, right? That means that this thing here, negative it in brackets squared, is just equal to positive it in brackets squared. So using this fact, we end up with ri it squared minus ri it squared, which is obviously 0 because we have one term take away the same exact term and you get 0. So we end up with 0 in the integral in the end, and the integral of 0 is just 0. It's just a fact that we all know. Integrals are just, you can think of them as areas. The area of a non-existent area is 0, of course, and you're left with negative ri0 squared over 2. That's just obviously 0 because 0 just nukes everything, plus 0 equals 0. And from this implies that the sigma, as z goes from 1 to infinity, of rizz equals 0, which means that we can conclude you have no Rizz. Okay, that's for option 1, where z is our index of summation, right? The next option is where I is our index of summation, rather than being the imaginary complex unit. So number 2, let me zoom in. The sum as I goes from 1 to infinity of rizz equals, let me just tidy this up a little bit, rz squared I. Same exact thing, I just put the variable I at the very end, or the dummy variable if you like. This is just equal to negative f of 0 over 2. I'm going to copy the formula down again and again. If I copy the formula down like 10 times, even you guys, the viewers, will probably end up accidentally memorizing it. Okay, so in our case, we have that f of index I equals to rz squared I. So we end up with negative f of 0 is just rz squared times 0 over 2 plus I, lots of our integral. I'm going to copy down the denominator and the dt as usual. The numerator is what we will work on. So let me bring this over there. F of it minus f of negative it in our case is equal to, if you replace this I over here and over here with this it over there and this negative it, you end up with rz squared it minus rz squared times negative it, which if we work on this a little bit more, we get rz squared it minus, okay, you see this minus here and this minus here? These will cancel to make a positive sign. So plus rz squared it. Whoops, what have I done? Rz squared it. Giving you 2rz squared it because I'm adding the same thing twice. So I'll put the 2rz squared I in blue and then the t in black, as the rest of the integral should be. Okay, now the first term, we have this 0 over here, which just nukes everything. We end up with 0. Plus I lots of that weird integral. So as I said earlier, this bit in blue is a constant, it's a scalar, we can just bring it outside the integral. We get 2rz squared I multiplied by I. And then the rest of the integral is going from 0 to infinity of all this, okay? This bit here, I squared, is obviously negative 1. I've said that before. We get negative 2rz squared times this integral over here. Does this look familiar to you? I mean, it should, because I've already done it over here. I mean, I didn't do it fully. I glossed over the details because there's not enough time for today, but that integral is the same as what I've boxed in red to be 1 over 24, as I've written in blue. So that integral can be replaced by 1 over 24, this purple bit here, 1 over 24, right? And if I simplify this a little bit, you end up with negative 2 over 24 is a 12th, rz squared. Okay, so this implies that the sum as I think our I was our index, right? Yep. I goes from 1 to infinity of your Rizz, according to the Ramanujan summation, is equal to negative 12RZ squared. Okay. Now, let's see. Let me go up a little bit and let's look at our parameters. We had R and Z. I said R was a positive real number and Z was a real number. So let's go back and see. Well, R is a positive real number, which implies that R is greater than 0. Z is a real number, which implies that Z squared is greater than or equal to 0. These two facts can allow us to gain the fact that RZ squared is greater than or equal to 0, which means that negative a 12th RZ squared is less than or equal to 0. This is because this negative sign here will end up switching the inequality sign from greater than until less than, right? That's just how signs work. The signs are flipped by the negative sign. And from earlier, negative a 12th RZ squared is just equal to sigma I from 1 to infinity of Rizz. This is less than or equal to 0. This therefore implies that you have negative Rizz, right? Negative Rizz, which means that you have no charisma, which can therefore conclude that you have no Rizz, right? So that's our mathematical proof for that way of doing things. However, to be 100% certain that everything is matching up, we have to use the third possibility, where we have our Rizz inside the sigma, but this time R is our index of summation. So sigma as R goes from 1 to infinity of Rizz is equal to, I'm just going to rewrite this, just rearrange the terms like this. By the way, I squared is minus 1 in this situation, right? Or I is root minus 1. I is not our index anymore, so I'm treating it like it were a regular constant. Now, once again, this is like the third or fourth time reminder that the formula for this is negative f of 0 over 2 plus I lots of this quite wacky integral, which is probably not weird anymore because, you know, you must be familiar with this now. So I'm going to write our function f of r equals iz squared r. Cool. Now let's do some working out and see what happens. So negative f of 0 is iz squared times 0 over 2. And we get that the denominator is like this. The numerator is what we have to work on. So this bit here, f of it minus f of negative it. This numerator is equal to, well, what we need to do is replace the r with the it and the negative it. So we get iz squared times it minus iz squared times negative it, which is equal to iz squared it, right? And this is a similar situation to before. This minus and that minus over there multiplied to make a positive 1, because minus 1 times minus 1 is just positive 1. So we end up with 2iz squared it. And if you collect the like terms and multiply them out, you get 2I squared z squared t. And I squared is minus 1, by the way. So minus 1 times 2 is minus 2 z squared t. So I'm going to reinstate that into the integral here instead of the numerator. And let's keep working on this. So as always, this will just be 0 because 0 times all of that stuff is going to be 0. Plus I integral from 0 to infinity of negative 2z squared t. You know what? This green bit here, this constant here, this constant term, I'm just going to bring it to the front just so that it doesn't disturb me. And this negative 2z squared doesn't depend on t whatsoever. So it doesn't need to be in the integral where it could distract me. negative 2iz squared is on the front now. The I was just already there, by the way. And then we end up with a familiar face. This integral from earlier, once again, is equal to 1 over 24. So just as I had, where was it? I dealt with it over here. This was 1 over 24. Okay? So if you multiply everything out, you get negative 2iz squared over 24, which is negative 12iz squared, which, as a reminder, this was the sum as r went from 1 to infinity of riz z. Okay? Now, to continue on with our proof, we know that I is a complex number, right? We know that z is a real number, so that z squared is positive, okay? This means that iz squared, well, first up, iz squared isn't even real. And second up, if you take the absolute value of iz squared, this will be positive, I think, right? You know what, let's not get into that. But if iz squared is not real, then this implies that negative a 12th iz squared is also not real, or it's imaginary, which means that sigma of r from 1 to infinity of Rizz is also not real, or it's imaginary. Which means that your Rizz is imaginary. Okay, so now I have proven the initial statement that the video of the title follows. Please give me feedback on the video, give me likes, subscribes, share this as well. Hopefully, if this video blows up as my pizza video did, and if I'm able to get the right amount of subscribers, I could start getting monetized. I just need to surpass 1,000 subs and I should be fine. So if you haven't subbed yet, please consider it. You really don't lose anything. It's a win-win situation because you get educational, humorous content. I get someone's support. So thanks for watching and hope you have a nice day.